Thanks, Francis. So this is a study I've been working on for my PhD, together with my colleague Erik Solbu and my supervisors Bob O'Hara, Francis, and Knut Hofstad. My motivation for doing this is that a lot of the ordination methods and geosdems out there often assume that species have equal tolerances on the environment or a linear response. But for almost 100 years, we've known that this is not the case. Very typically, we know that by some species being a specialist, some being generalists. So it's this idea of this graph here, where we have an ecological gradient on the x-axis and abundance or occurrence on the y-axis. U being the species optimum and T being the tolerance. And as you move further away from the optimum, the conditions for the environmental conditions will be less suited for the species up to a point where you won't find it at all anymore. So we want to model the ecological niche. So I'll be talking about unconstrained residual ordination, also known as GSDMs, where we're assuming a quadratic response curve to relax this assumption of equal tolerances. And we treat the ecological gradient as unobserved, as latent. Where here in the second figure, you see these two different colored species, where the blue species clearly has a smaller tolerance than the green species. So you could think of the blue species as a specialist and the green species, the other way around, blue species as a specialist and the green species as a generalist. So here I have three tolerances model where we have two ecological gradients on the x-axis and again, abundance or occurrence on the y-axis. Where the first row of plots shows the equal tolerances model, where we have unequal maxima, so the height of the curves, and optima on the ecological gradient for the species, but the tolerances are all the same. And on the second latent ecological gradient, we have the same tolerances for all the species, but again, different optima and maxima. Then the middle column shows the common tolerances model, where we still assume the tolerances to be the same for all species on the same ecological gradient, but then on another ecological gradient to be different. And then we have the full unequal tolerances model, where maxima, optima, and tolerances are different for ecological gradients. So there's a couple of methods that relate to estimating tolerances when the environment is unobserved. So most typically correspondence analysis, which is known to approximate the equal tolerances model and making some additional assumptions, fitting or approximating the species packing model. And then you have some model-based methods where with mixed models, you can also fit the equal tolerances model. VGLMs, same thing, also equal tolerances. And then most recently, the R package RCM, which can also do unequal tolerances. But the authors very clearly state that this is only meant for data exploration, because due to the constraints on the parameters, you don't actually get a maximum likelihood solution. They only implemented it for count data, and their response curve can actually be convex, which is what we didn't want here for ecological reasons. Then we also have the generalized linear latent variable model, where if you add a site-specific intercept, you also fit an equal tolerances model. But in general, it's hard to actually retrieve the tolerances from these methods, as they're hidden in some other parameters. So we here also focused on GeoLVMs, which is this vector analytic approach that everyone talks about, that you can understand as GSDMs. And Francis and colleagues pointed out in 2014 that you can also do model-based ordination with this. And then additionally, in comparison to more classical ordination methods, you can include covariates or functional traits and row effects or site-specific intercepts. And we treat the latent variable as random. So it's a type of mixed effects model, as noted before. What I'm doing here is based on the GeoLVM package by Jenny Nikio and colleagues, which implements these models using approximations to the marginal likelihood, so either Laplace or variational, in combination with template model builder to make everything run nice and smooth. So the quadratic GeoLVM, where we, sorry about that, where we have this matrix of observations per site and species, species-specific intercept beta not J, the latent variables that we assume to follow this multivariate standard normal distribution, the linear coefficients on the linear term. So this is essentially the linear dual-LVM, and then we add quadratic coefficients in a positive definite diagonal matrix per species. And then the common tolerances model is the same as assuming that this matrix D is equal for all species, and the equal tolerances model assuming then that the diagonals is all the same coefficients. So that gives this equation 1, where the first two terms, essentially the linear dual LVM, and then we add this extra quadratic term that's negative only to produce these concave shapes. And from this model, we can derive the tolerances and species optima. So essentially, we then get unconstrained quadratic residual ordination or a JSDM with quadratic latent variables. But since the latent variables are treated as random, we need to integrate them out. So for that, we used variational approximations because Laplace wasn't suited. And Francis and colleagues wrote an approach to the linear dual of LVM 2017, which we here extend, where we have a vector of parameters theta. And now we assume that Z follows multivariate variational distribution with a site-specific site and latent variable specific means, and this variance covariance matrix. And then we have the log likelihood for the quadratic dual of M in equation 2, where we have this first line, which looks suspiciously similar to a GLM, except for some of the expectations. And then the second line that is due to the VA approximation. And we did this for the Poisson negative binomial and gamma distributions, Bernoulli and ordinal, and the Gaussian distribution. And then we plan to add this to the dual VM package as well. So I fit an example data set, the spider data set by von der Aert, which is often used in assessing new ordination methods, which has 12 species of hunting spiders at 28 sites in Dutch dunes. I just fit in around 6 seconds. So it's pretty fast, but it's a small data set. So this has counts. So we fit this with a Poisson distribution with 3 latent variables, in contrast to in the linear dual LVM, where you generally fit a negative binomial distribution with 2 latent variables. And then we have here this figure on the left side, where we have the first latent variable on the x-axis and prediction on the y-axis. And then you get these very nice quadratic curves with confidence intervals for each of the species. Then in 2 dimensions, where you still have the first latent variable on the x-axis and the second on the y-axis, you can visualize the species optima here by the species names. And then we can use the tolerances from the quadratic term to create these species distributions in latent space. And you can, of course, think about what it means when these things overlap or not. So I fit another data set, which is here shown on the right, with 175 species and 730 sites, which fits in around 45 minutes. These represent absence of alpine plants. And then we see this kind of caterpillar-like plot that almost looks like a tornado, where we have small tolerances here on the bottom and larger tolerances here in the top. We have to note that, of course, anything above 1 extends beyond the latent variable. But it's clear that these tolerances are estimated to be unequal, and the same for the spider data set. We have these kind of 3 groups of species with different size tolerances. The residual covariance matrix is calculated like this, where we have the elements of the residual covariance matrix, the sum over the latent variables, quadratic term in the linear coefficients, and the same in the quadratic coefficients for different species. And since this second term is due to the quadratic model and it's positive only, this means that the model emphasizes positive species associations more in contrast to the linear dual LVM. We can also see that here, where I have a plot of the residual correlations between the species of the spider data set. And then I have the lower triangular are the residual correlations of a linear GeoLVM with the same number of latent variables. And the upper triangular is from the quadratic GeoLVM, where you can clearly see that there's here a lot more negative residual correlations, a lot more red. And if you look here, then a lot of them have disappeared or are a lot weaker. So to conclude this fast presentation, GeoVMs I think are quite awesome, very cool method. We have this cool fast method as well that we extended. And environmental tolerances are unequal. So start considering if it's appropriate to assume that they're all equal. That's it. Thanks.